So for my project, I will be diving into three main topics of calculus: derivatives, integration, and volumes by rotation. So starting off with derivatives, a derivative can only exist if a function is continuous, as if a function is differentiable, it thus must be continuous. So what is a derivative exactly? Well, one, a derivative can be seen as many things, but essentially a derivative is just a slope of the function, and a second derivative is the slope of the slope, which is the concavity. So let's start off with finding a derivative. Here we have a problem of f of x equals 6x squared plus 2x plus 12x plus 8. Okay. And in order to find a derivative, this is just simple power rule. So our notation is f prime of x equals to 12x plus 12, and that's it. So for power rule, what you do is you bring down the exponent and then you subtract the exponent by 1. So from here to here, it is times by 2, and 2 minus 1 is 1. Times by nothing, times by 1, and then subtract by 1, and x1 of anything to the power of 0 is 1. Same here. Since this is a constant, the derivative of a derivative of a constant is always 0. So right here is the next function, and it's much more complicated as we have two rules: chain rule and product rule. So in order to do this derivative, we do f prime of x equals the derivative of the first one, which will be sine of x, which is derivative of sine of x is cosine x times cosine of x squared, plus, and then we do first times second derivative, or the first part times second part of the derivative. So sine of x times the derivative of cosine is negative sine of x squared times the inside derivative, which would be 2x. And that there is numeric. And if you wanted to find the derivative of, say, x equals to 6, then you do f prime of 6 equals to cosine 6 times cosine 6 squared plus sine 6 times negative sine 6 squared times 2 times negative 6. So what's that? Majority of the times. Okay. And this right here is it's kind of complicated, but it really isn't. Since we see as we see, the functions are a fraction. And in this case, we would just do something called quotient rule. Quotient rule can be summarized as low d high minus high d low over low squared. What this means is that we take the function of the low, the bottom one, we bring it up, times it by the derivative of the second one, of the high, minus the high function times the derivative of the low function over the function of the low squared. So our notation, f prime of x equals to low 7x squared plus 3 times the derivative of 3x squared plus 2x, which would be 6x plus 2, minus high, which is 3x squared plus 2x, times the derivative of low, which would be 14x plus 0. You can just cross that out, but sometimes it helps me understand it. Over 7x squared plus 3x squared. Simple as that. Moving on. This right here is a natural log. And natural log is pretty simple in its understanding. So in order to do the derivative of a natural log, it will be 1 over x. So f prime of x equals to the first part, 1 over 2x squared times the inside derivative, which would be 4x. That's it. And if you wanted to do the double derivative of it, 4x over, sorry about that, 2x squared, which is simplified. And if you want to do double derivative of this, it will be f prime of x equals to low d high, so 2x squared times 4 times, minus, high d low, 4x over times 4x over 2x squared. Simplified, it will be 8x squared minus 16x squared over 4x to the 4th. Pretty much like that. Overall, derivatives are pretty easy, but when it comes to the graphing part, that's where it really comes at it. So, right here, let's say that our function has a derivative, and this is f prime. We notice that from negative 3 to 3, the concavity of this is concave down. And we notice that at negative 3, the x is always increasing until this point. This point we'll just say is x equals 1. So at x equals 1, it changes from increasing to decreasing. And also at x equals negative 3, it goes from negative to positive. What does that mean to the graph of x exactly? In summary, in order to deduce what the graph of f of x will look like, we follow the rule of f of x plus minus increasing, decreasing, up, concave down. F prime of x and f double prime of x. F prime of x plus minus increasing, decreasing, concave up, concave down. Continuing on. Now notice how the positions of each of these are where they at. So f of x, let's say that at x equals 0, it goes from positive to negative. That doesn't really change. It says that it is increasing from 0 to 1. Okay, let's just say that that's the graph of f of x, my bad. If f prime of x, if it is positive at a region of, let's say, 0 to 1, then f of x would be increasing from the x of 0 to 1. Continuing on, f prime of x, let's say from 0 to 1 was positive. That means that f prime of x will be increasing, thus f of x would be concave up. And we notice here that at x equals negative 3, it goes from negative to positive, meaning that f of x is going from decreasing to increasing. Decreasing to increasing means this to this. This to this. And that produces for f of x a concavity of up. Meaning that at x equals negative 3, a critical point, there will be a relative min. Moving on, at x equals 3, we notice that it goes from positive to negative, meaning that f of x will go from increasing to decreasing, yielding a concavity of down. Thus, at x equals 3, there must be, or some form of, relative max. Okay, yeah. Moving on. Let's say for a different function, f double prime is this graph presented right here. So at x equals negative 4, these points right here are called inflection points, meaning that the concavity of their graphs are changing. So we notice that here, from the left of x equals negative 4, f double prime of x is positive. And from down here, it is negative. Continuing on from here, it will be also negative and positive. So at x equals -4, since it's turning from positive to negative, f of x be going from, as shown here, concavity of up to concavity of down. And from here, since it's going from negative to positive, it will be concavity of down to concavity of up. So what I'm trying to say is that if there are zeros for a graph of f prime of x, f double prime of x, those are called inflection points. All they really mean is that the concavity of f of x is changing. And over here, for f prime of x, these zeros are called critical points. They're basically where concavities are being developed or formed. Like right here, there's going to be a concave of up, and over here, there's going to be a concave of down. That sums up derivatives to my degree. It's not a good explanation, but it gets the point across, kind of. Moving on to integration. Integration can be seen as the antiderivative, essentially what it is. So the rule for integration is we follow this definite function in which the integration symbol of 0 to 4 from a to x plus 7 dx. So the rule for integration is that you do +1 to the exponent times, and then bring down the exponent, the reciprocal of it. So this would be 8 times, notation, equals to 8 times 1/2 x squared. As you add 1 to the exponent, which would be 2, you bring down the reciprocal, which would be 1/2, plus 7x. Since 7 was a constant, the only antiderivative it could have would be a extra x, as it doesn't have it. And then from the line of 0 to 4. Simplified, this would be 4x squared plus 7x from 0 to 4. And in order to do integration, you do, which equals to 4 times 4 squared. You plug in all your x's, parentheses minus and this yields, since the x's are 0, this can be just considered crossed out, but make sure that like when you plug in x, it does yield 0 as an answer. Since let's say that if there was a constant, a random constant, then that could actually really affect the answer. So this right here is numeric, and this shows that the integration from 0 to 4 for 8x plus 7 is this. Pretty simple as that. Moving on, we have an indefinite integral. Now, indefinite integrals are really weird, in which you have to do plus c at the end. Remember that, plus c. So, since this is 1 over 2x, and x has no exponent, we know that this antiderivative must be natural log. So we do natural log of 2x times the inside derivative, the reciprocal of the inside, which would be 1/2, plus c, since we don't know the boundaries. And we know that it is 1/2 because if we do the derivative of this, 1/2 ln 2x f of x. Let's say this is the function, and we do the derivative, it would be 1/2 times 1 over 2x times the inside derivative, which is be 2, which equals to 1 over 2x. But since we don't have a constant, we don't know what the actual function really is. Over here, we have a more complex function, in which we have the integration of from 0 to pi 2x sine x squared dx. Now we notice that since there are many parts to this, we can't really use these methods as shown before. But we can use something called substitution method. We find a common thing like x squared, let's say. So u equals x squared. The du, or the derivative of that, would be 2x. As we notice, is up here, dx. And since we're doing this in terms of u, we had to put these into terms of u too, the boundaries. So u of 0 equals 2 x 0 squared, which equals to 0. U of pi equals to pi squared, which equals to pi squared. So these will be our new boundaries for the new function. Integration from 0 to pi squared of u sine, of sine u du. Right? Yeah, because the du replaces the 2x dx and the u replaces the x squared. And then we continue on, which what is the antiderivative of sine of u? Well, the antiderivative of sine is negative cosine. So we have negative cosine of u from 0 to pi squared. And then we continue on, we come back with u, and u equals to x squared. So it is negative cosine of x squared from 0 to pi squared, which equals to negative cosine of pi squared minus negative cosine of 0 squared. So yeah, that is numeric, but if you want to simplify it, this part can be simplified as, since 0 squared is just 0, and then the cosine of 0 is just 1, so it would just be equals to negative cosine of pi squared minus negative 1. Voila. Integration is basically just the anti-derivatives of a function. Sorry, my phone is bugging out. Moving on, integration can also be seen through Riemann sums. Hold on, I'm gonna charge my phone real quick. Sorry, Mr. Bridger, this is really scuff. Focus. Okay. So what integration basically is it consists of large amounts of Riemann sums to find the area of a graph. That's what integration is, the area of a graph. So let's say that we have a right Riemann sum, and this is our table. And it says to find the right Riemann sum for four parts. So the formula for Riemann sum is, we do integration from 0 to 12 of f of x dx, notation, which equals to the distance of the spaces, so 5, and since this is a right sum, we do the right term, f of x. So 8 plus the distance between 2, which is 2, times the right term, which is 15, plus the difference between that, which is 3, the right term, which is 20, plus the difference between this is 2, and the right term is 22. And that is your right Riemann sum. A right Riemann sum looks like this. So let's say this is your graph. It basically is when the rectangle hits the right point.